Good afternoon, ladies and gentlemen, and welcome to this clip where we explore a new spring workflow in Prokon SUMO. My name is Jacobus Oberholster. I'm an AEC and Prokon technical consultant with Micrographics. And you can check my email address there in the bottom left-hand corner. You are welcome to reach out to me if you have any questions. Either send me an email or pop them in the comment section below. And if you haven't subscribed to our channel, please do so. And remember to like this videos. It really goes a long way in just increasing our exposure to the market. So without further ado, let's jump into our clip for today. So in a previous clip, we actually looked at some new functions and workflows in ProConsumo. And in that clip, I mentioned that we'll actually be taking a deeper dive into the new Spring workflow available to ProConsumo subscribers. And so here we are. And also, just what we'll probably further on do, or do further on rather, is that we will look at a deep dive into the Spring workflow in a later clip. But we'll just do an introduction in this clip, look at some of the basics, and then in a later clip, we can actually look at how you would integrate data from an actual stiffness analysis that we would conduct in something like Ideostatica connection, import that data into ProConsumo, and then look at the change in results. All right, let's just have a quick look. If we look at the structure tab, you'll see that there's a new point command up there. And then as well, you should see two new tables available, which is spring laws and spring definitions. So what we'll do first and foremost is I would just like to set this, let's keep it as a normal linear analysis type for now. I want to run my analysis. Of course, I've just excluded self-weight for simplicity. We can go to results and we note that there is a uniform displacement of 15.952. Of course, they are exactly the same members. They are fixed exactly the same way and they have exactly the same load. So what we'll start off by doing is looking at our spring laws. We'll add a spring law. You can see it has a name. We can add some notes, and then there's a degree of freedom. So there's translation and rotation. For this particular one, we might actually look purely at a rotation degree of freedom. And then we need to look at the parameters. So if I click on linear, you can see this is where we determine our stiffness graph. We can set that it is symmetric, meaning it's the same top and bottom, so for both positive and negative displacement, or we can adjust that they actually displace differently depending on which direction the displacement is. Now, why would that be the case? Well, you can imagine that if a connection is being bent upwards, depending on what its geometry looks like, it might behave differently versus it bending downwards. Now, this can just be as simple as a beam connected to a column with an end plate, but that end plate extends further down at the bottom of the beam than it does at the top. So, of course, that connection is not symmetrical about its x axis in that particular case. So it will have a different stiffness upwards than what it would downwards. So in this case, we can adjust those values. So we can maybe set this to something like, let's say 1,500. And for now, I'll keep it symmetrical. In our deep dive, we'll actually look at this in a bit more detail. But over and above the stiffness value, you've got three types of graphs. You've got bilinear and parabolic, and we'll also look at that in a later clip. All right, I have my spring law. I can just say this is for a standard beam to column connection. I then go to my spring definitions. I need to add a definition, and I can set in the type of spring. I can assign a spring law to these different translation directions as well as rotational directions. Now, of course, if a spring law is a rotational spring law, then you can't assign it to the translation definitions. Unfortunately, the program at this stage allows you to still select that spring law, but you will actually get an error if you assign a rotational spring law to one of the translational definitions. So over here, I'm just going to set this as spring law 1. It doesn't have to be assigned to all of them. You can just assign it to one direction only. We might get an error and have to come back and assign a translational spring law as well with just an incredibly high stiffness, but we'll look at that. So right, with my spring laws and definition, or rather spring law and spring definition defined, I can now go to the structure tab ribbon and springs panel, click on point, and then place that spring over there. So of course we've got the spring. You can see that the local axis is what is relevant to these translation and rotation directions. So just note that. And of course, you can just see the colors match up with that of the global axis. So you know that blue is Y, uh, green is Z, and red is X. What we need to do next, just before we do that, you can actually change its orientation. So you can see you can adjust the orientation. But what we need to do next is to define the head and the tail, or rather tails of this spring. The head in this case, you can only assign one element to the head. It makes sense that it is the column, and then we need to assign a tail as well. I just want to see which one is which. This is beam 1, so I'm going to assign beam 1 as this tail over here. All right, I'm going to leave beam 2 out. For any spring element, you only have one head, but you can have essentially an infinite number of tails. I'm going to exclude beam 2 because I still want beam 2 to displace as per normal. Lastly, we have to assign a spring definition to that tail, and then we can hit OK. All right, here we see that there is an error, and you see that all connecting elements need to be assigned to a spring node. And of course, now that means that we actually cannot exclude this member here. So what I'll do in this case is I'll add a tail and assign beam 2 and assign no spring definition. Let's see if that's okay. Again, it's critical. So unfortunately, you have to assign a definition. So in that case, say for instance, you don't want this beam to, you actually don't want to consider, you want the stiffnesses to be as per normal, meaning if it's fixed in a sense and an infinite stiffness, I'll define a second one. I'll call this infinite stiffness. I'll make it rotation and then linear, and then I'll make this value 10E6. So just an incredibly large stiffness value. And you can actually something that you can test out, where you can test different stiffness values to see how stiff is a fixed connection, actually how stiff is a pinned connection. Actually, very, very interesting. Of course, a pinned connection has got 0 rotational stiffness, and a fixed connection has an infinite, essentially an infinite rotational stiffness. So, all right, let's go for that and to assign these definitions. So in this case, I'll go for spring law 2. We might have a problem with these translation definitions, and we might have to define an additional spring law just to assign an infinitely stiff translational definition here. So, all right, I think that's fine. Let's assign that definition 2 there. It seems we're okay. And let's see if this runs. It might actually give us a problem. Let's have a look. Okay, so this is most likely due to the fact that we don't have any translational stiffness. So I'm going to define a third one, and let's make this infinite rotational stiffness. We'll make this one infinite translational stiffness. All right, and we'll set these values to 10E6. All right, we'll go to spring definitions, and we can assign this to all of those guys. All right, so this side should deflect less than that. This side should deflect more. It's not as stiff rotationally. So let's have a look. Okay, so you can see that the analysis ran, and there you will note a difference in how the two deflected. So this side is 15.962. And if you remember back to the start of the clip, when we just had these normal fixed ends without a spring element there, the displacement was 15.962. On the right hand side, the displacement is 75.953. Right, very, very cool. I am going to remove this element. We can run our analysis again. You'll see in this case 15.952. All right, so that's it for the introduction to the new Spring workflow to Prokon SUMO. Please check out or have a look for the clip where we look at a deeper dive into this. That should be in November at some point there. So please make sure you subscribe to the channel and hit that notification bell so that you get notified when new clips get released. We also cover a ton of Ideostatica content. We cover robot content, advanced steel Revit, you name it, we cover it. If there's anything specifically you'd like to see, please pop it in the comments section below, or if you have any questions, otherwise reach out to me via email. I'd love to hear from you. But other than that, I hope you found this interesting and you have an awesome afternoon further, and I look forward to seeing you in future clips.